Okay. So I'm Dimos, and the first question I have to respond to, I think, is why Dynamo? So Dynamo was one of the papers that I first read when I started looking about distributed systems, and I got really excited. And the main reasons is, first, they didn't really invent something new. Most of the algorithms were pre-existing, but they showed how you can compose them all together in a tool. And that was what was really interesting for me. And the second one is, most of these algorithms are quite complex, and when reading about them, you have to scroll back to the history and read more papers to understand what's going on. But the way they present it, it's easy to understand what they're doing, even though you might not understand completely how they work. You can understand what's the use case of its algorithm. So today I will try to go over some of the techniques they present in the paper and explain as easily as I can how they work and what's the use case. So before starting with the techniques, I would like to provide some background, some context on what was happening in the era when the paper was written, so that we can understand why they made some decisions. So at that point, most of the people were building three-tier applications where they have, or two-tier, let's say, where they have the application layer and the stateful data store. They were reading and writing to that store, and at some point they needed to scale up. And the way they did that, usually, is they added some read replicas to their database, and every time they kept writing to a single instance, which was, let's say, the master or the primary, and writes were propagating to the other replicas, most cases synchronously. So by that, they were achieving two things. The one is they were making their setup highly available, because when the primary was failing, they could read from the replicas. So it was highly available in terms of reads. And also, the reads, the latency of the reads was lower, because reads could go to all the instances and not only to the primary instance, which would be overloaded because it would also have to tackle the writes. So that was the setup. They were writing only to the primary, and they were reading from all the instances. And the problem with that approach was, first of all, as we previously described, reads, they could scale reads very nicely, both in terms of latency and availability, but they couldn't do the same for writes, because they still had a single point of failure, and it wasn't highly available, and all the writes would go to a single instance, so they would get slower with the time. This is essentially the same. It was mostly a read-friendly architecture and not write-friendly. There was some overhead that was arguably needless for applications that only need other drawbacks. And the last one is, it was far from the vision Amazon had at that point for auto-scaling. So every time they wanted to scale out their application, they had to do a lot of manual work to add replicas and then set up the replication, etc., etc. So they wanted to have something that was that would be able to scale automatically. And one of the applications that was the primary use case for these new data store was the shopping cart application they had. So that application was responsible for storing the cards of customers, and could easily be modeled as a key value operation, where the keys were the session IDs of the customers, perhaps, or the cart IDs, and the values were all the items of the customers, of a specific customer. And for that application, what they needed is extremely high write availability, because no matter what failures they had, in their environments, they wanted customers to be able to add items in their shopping cart because that's where they get money from. And they wanted also to that operation to be very fast. So these were the driving factors that led them take the decisions they took for that system. So this is a very simplified architecture of how the system worked like before we go into the details so that we can have an idea. So the way it works is you have an application. The main two operations are get by a key or write a specific value for a key. And then essentially what they did is they split their dataset. They sharded their dataset in multiple datasets. And we can see that for simplicity, I did that alphabetically. And for each part of the dataset, they had a number of replicas that contain copies of that dataset. And both reads and writes could go to every single one of the replicas for each dataset. So when they wrote Bob, any of the replicas in the first group could reply to that, even if it was a read or a write. So that was an overview of the architecture. And to do that, they had certain obstacles, and they solved them through some techniques. These are those techniques, and before we go on detail for every technique, let's describe briefly the problem. So partitioning is about deciding on which group that we saw the data will go at. The next problem they had is, as we explained, they wanted to have very high availability for writes, and they went to extreme length to do that. We will see later on. And they also wanted to recover from failures, either temporary failures, for example, servers that would temporarily crash and come back again after like 5 seconds, and permanent failures, like servers that would crash and never come back and they would have to be replaced. And the last one is, as they were going through a movement to an auto-scaling system, they wanted to be able to have an easy way to detect where nodes were dying and where nodes were coming in the system and incorporate them easily. So first problem, partitioning. The easiest way to do that is what we showed before. Sort the dataset alphabetically and then create shards of that and then have an application that maintains that mapping. The other approach that most applications use, and is better to distribute your data more uniformly and not have hot datasets, is regular hashing. So essentially what you do is, as an n, you have the number of the servers, and then k is the key, you hash the key, and then you do a modulo operations, the number of the servers. And with that you decide on which server an item would go, if it's a write, and on which server an item could live or could be retrieved from, if it's a read. The problem with that approach, one of the problems, is as we see there, when you want to scale up and add one node, there is a lot of churn, which means all of the associations will change, or a very high percentage of that. And that means that auto-scaling will not be very efficient. You'll have to move a lot of data around. So that was one of the problems they had to tackle. And the way they tackled it is through a technique which is called consistent hashing. What that is you use the same approach, but you twist it a little bit. And you assign a random number to every server in a specific range from 0 to L. In this example, I took 360 for L for simplicity, but it should be much higher to be able to stretch it when you add a lot of servers. And then what you do is whenever an item comes in, you hash that item again, and then you do a modulo the size of your range, and then you find the next server from that point on. That is the server that will have that item. So if the key Bob comes in and the hash is the one shown there, the modulo is 72, and the next server after that is the server 1 at 90. So this is the server that would contain the key. And one way to do that, again, is maintain a sorted mapping from numbers to the servers. And then with a binary search, you can find which server is the right one in a logarithmic way. So what we were discussing previously is the problem that regular hashing has when you add a server. So how does consistent hashing solve that? So when a new server comes in, you assign a random number, let's say 140. And in that case, server 5 would get all the data from server 2 that are between 90 and 140. So data transfer between only 2 nodes. So it's much easier to scale the system. Another problem that comes in here is that it can get quite unbalanced, right? So what they did to improve that is, instead of having real nodes, they had what they called virtual nodes. So that meant that each circle you see here doesn't necessarily correspond to one server. So one server could get 2 or 3 nodes. And that would again distribute uniformly the load between the servers. And when a new server comes in, that means that because the numbers are really high, data would be exchanged uniformly between the servers. You can get more details in the paper about that. So the example we saw before was simplified again. So the real version is that they wanted to have 3 replicas or n replicas of the data set, right? So instead of just populating the data in the next server on the range, they populated in the 3 next servers. And since they did that for the reasons we explained previously, high availability and low latency, based on the fact that they would be able to read and write from multiple servers. But they also wanted to have some form of consistency. So they wanted to be able to give a guarantee that there would be a way to get the latest version of an item, no matter what happens on the system. And that would be hard if you have multiple replicas where all of them accept writes. And the way they solve that problem is through quorums. So what they did is, as n here, which is called replication factor, is the number of servers that contain a copy of an item. In our case, it's 3. For example, in the left example, R is the read quorum and is the number of servers that have to reply to a read to consider the read successful and give it back to the customer. And W, in the same sense, is a write quorum is the number of servers that have to reply to a write to consider the write successful and give it back to the customer. So if they made sure the system always satisfied the equation R plus W greater than N, that meant that at least one server would have the latest version. So if we have 5 servers, so N equals 5, and you try to select 2 sets of 3 servers, then at least one would collide, would be in both sets. That's the main principle under that. The way they guaranteed that at least one server would have the latest version. And there is a small caveat there, which means that even though this implies that there is strong consistency, there is a very edge case where it doesn't. I won't go into detail now, but if you're interested, you can ask me in the end, and I can explain. It's quite interesting, but it takes more time. So based on the fact they had, based on the quorums we saw, different servers had different versions of an item. So when they had that conflict, they had to find a way to identify what's the right item, what's the latest item, right, to return. And they use an algorithm which is called vector clocks, or a data structure, let's say, to solve that problem. Before we see how they solve that, let's get an introduction to the problem, to the algorithm first. So the main idea of the algorithm is that you have multiple actors in a system that exchange events between them. And you want to have a way to identify for two events whether one was the cause of the other ones, whether one led to the other one, or whether they are completely independent. So the way you do that is you have a vector of integers, one for each actor, and that is maintained by all the actors. So that vector starts from 0, and every time an actor sends an event to another actor, it increments the integer for its own clock and sends the whole vector to the other actor. In the same way, every time an actor receives a clock, it maintains the maximum for each integer. It maintains the maximum between its own clock and the clock he receives. So based on that, when you have two events, you can identify whether, so you have events A and B, and you can identify whether A is the cause of B. That holds true if and only if all the integers of A are less than the integers of B, and at least one of them is strictly less than the equivalent integer on the other one. So in the diagram we're seeing there, what the colors mean is that all the events in the blue area are actually causes of the event in the middle that has B4. And the event with B5 is the cause of all the events in the red region. So if you go through the equations that I gave you of the algorithm, you will see how that is identified based on the equation that I gave you. So how did they use that? What they did is each actor in their system was one server, one replica node, and maintained a vector clock, as we saw. So this is the diagram they give in the paper, and in my opinion, it's not very clear. So you have to spend some time to understand what's going on here. So that's what I'm trying to do now. So let's say first write comes in, it goes to node D1, it increments its clock, which is SX to 1. Then a new write comes in, D2 handles that. The same SX handles that again, increments its own clock again to 2. And then at that point, two concurrent writes come in, and they're handled by two different servers, SY and SZ. And they both increment their clocks to 1. And next, final request comes in and comes to SX. And at that point, SX investigates the two versions, D3 and D4. And it applies the same algorithm we saw on the left. And by applying that algorithm, it identifies that there is no causality there. They are completely independent, so I have to do something. And at that point, there is a conflict. And the way they resolve that, so when there is a conflict between events that are completely independent, they return both back to the user, and the user says, I want that. That's the right version. And it gives it back, and server X overwrites with a new vector clock. That will be the effect of the other ones. So D3 and D4 are now causes of D5. So in any case where both are seen, there won't be any conflict anymore. D5 will say, the system will be able to say D5 is the effect, return back to the customer, to the client. So what's missing here, and makes it more complicated to understand, is that there is no client in the diagram, right? So there is one more thing that is missing on the left, that the system also contains a fourth actor, which is a client. And what happens is that this vector clock is passed back to the client and again to the system. It's passed between these two actors, the system and the client, to make all these checks. So when we see the first write being handled, essentially what happens is the customer receives that vector clock, and on the second write, it gives it back, right? Because essentially there are no events passed through the nodes here. It's only through the client and the nodes. That's the trick you have to understand how that works. So the next section is failures, how they handle failures. And there were two types of failures. The first one was temporary failures. And the technique they applied to deal with that is called hinted handoff. So we have these three nodes that would, in normal cases, receive the replicas. And the second of them is down temporarily, is having an issue. So what they do instead is they pick the next node and give that data to that node instead. That node will keep it in a table temporarily, and through they also have a protocol that we will see later on for knowing which nodes are up and down. So when that node, the fourth node, identifies that the second node is up again, it sends back again. The second node applies them, and the way that helps is, if you consider the setup we saw before, let's say you have a replication factor of 5, and you have a write quorum of 3, right? What that means is that you must have at least 3 nodes alive to get a write, right? 3 out of 5. With that setup, what you have to satisfy is to have 3 nodes alive out of the whole system, not the 5 that contain that replica set. So availability is much higher. You have the whole farm to leverage and give handoffs temporarily. It increases write availability even more. However, it poses some durability risks, right? So what happens, for example, if handoff is passed on to the fourth node, and before the second comes up, the fourth node dies. Data might be lost. So for that reason, they also had to deal with permanent failures. What they did for that is they synchronized nodes between them. Periodically they sent, so every node had a range of keys in his data set. And if there was an issue, some node would be missing some of the keys because of the issue we described. What they did is nodes between them periodically would exchange their key range. And if something was missing, they would exchange these missing keys and they would come back to a consistent state. The problem with that is this key range was very big. So if they exchange the whole key range, it would be a lot of data exchange. So what they did is they used the data structure which is called Merkle tree. And what that does is you get all your data, which in that case synchronized between them. They can initially pass the root of the tree, just one value. If the hash of the root is the same, then they both have the same data. They don't need to do anything else. If it's not the same, they check the children, and one of the children will be different, not both of them, right? So they find that children, and then they check his children. So essentially, they do a binary search in the tree. And what they can do with that is, instead of passing a linear size of data, they pass a logarithmic size of data, at worst case, when there is a difference. But when there is not a difference, they pass a really small amount of data, which is just the root of the Merkle tree. So, of course, a suspicious mind here would say that we can have collisions there. So that's not... the fact that they are the same doesn't mean that there is no difference, because there could be a collision there between keys, and the hash could be still the same. And that's true, but if you look for it in the internet, you will see that the probability of that is extremely high. It's some hundreds of power of 10 low. So the last section is membership and failure detection. And as we described, what that means is nodes were coming in and out of the system, and they dying and coming alive again, and they wanted to have a way to identify that. So before going in the solution, what most people do in this case is they have a centralized system where nodes can send heartbeats, and that system maintains a consistent picture of the whole system and can say which node is alive or not. And a system that some people use is Zookeeper, for example, for that. The problem with that is, again, it's very centralized, and the number of nodes in that system can get very, very large, and would probably not be easily handled by a few nodes from Zookeeper, for example. It's not very scalable because all the traffic goes to a single funnel again. So what they did is they tried to decentralize that instead of having a single store. And this is called, this kind of algorithms is called a gossip-based protocol, or dissemination, because it resembles the way diseases spread in the population. And the way it works is at every epoch, at every period, each node picks B nodes randomly and transmits its membership table, which shows which nodes are alive or not, and perhaps other data like when was the last time I saw that node alive, or things like that. And that goes on recursively. And every time a node receives that membership table, it synchronizes with its own data. And if one of the nodes has been seen dead, has not been seen live for m epochs, it is announced dead. That's the main workings of the algorithm. And to show how that works, if B is 2, that's the way it would work, for example. And this is a completely separate topic. There are many, many papers about that. But the main gist is that if there are no changes in the system, if no nodes are dying and no nodes are coming up again, then in a logarithmic number of steps, the system would arrive to a consistent state. All the nodes would have the same picture, the same view of the system. And there is some discussion in the paper that whether they needed to have, because in that setup, that doesn't hold true. There are always changes. There are always nodes dying and always nodes coming up again. So that means that every single node will have a different view. And there is a discussion in the paper whether that was okay for them or not. Initially, they thought it wasn't okay for them, but they eventually found that based on all their use cases, the system would work fine, even if there is no global view of it, and every node has its own view, which is eventually consistent. So these were the main techniques that they used, and one of the factors that I consider when evaluating whether a paper is valuable or not, it might not be the right way to do that, is whether there are projects using these techniques in practice, right? And two sample projects I picked up is Apache Cassandra and REAC. So Apache Cassandra, REAC is a key value store. It's very simple interface like key value operations, as we explained. Apache Cassandra is slightly more complicated. It's because instead of just the key, you also have what they call, you have a hash key and what they call a range key. So you can do some more clever operations, like for a specific hash key, find a specific range. It's a bit more complicated, but the main idea is the same. And as you can see there, both of the systems almost use all of the techniques. exactly as they're described in the paper, or with some small adjustments. The only difference is that Apache Cassandra isn't using vector clocks, and that's a decision they made explicitly because, as we on local clocks, and they have a last right wins approach, which is there are a lot of arguments in the industry. So what they do is when there is a conflict between two items, they pick the one that has the latest timestamp. So there is some risk there because there is clock drift, and that might not be the right item necessarily, etc., etc. But just calling that out. And I think, yeah, at that point, we arrived at the end. If you want to have a look at the slides, I posted them in speaker deck, so you will be able to find them there. Thank you. Is there any question?